Is it, the audio is clear and everything? Yeah. So, yes, any questions? So we are on, right? Yeah. So, any questions from last time? So we've had like a kind of a summary of ADS-CFT.
When you wrote the ADS-CFT dictionary, CFT was identified with the SUN invariant operators.
Right. So in the specific case, you know, so the statement of ADS-CFT correspondence, the general idea is more general, right? So like, see, for instance, it's not completely clear whether ADS-CFT, the dual CFT should necessarily be a gauge theory. In the examples that we know, always they have some boundary gauge invariance. But its significance is, I would say, still not completely understood. Why is it that the dual theory, all the known examples of ADS-CFT duality, I would say, have some form of gauge invariance on the boundary. But in principle, it looks like ADS-CFT kind of works, you know, the statement that I made regarding these, you know, this having a n parameter n or c, or sometimes it's in 3 dimensions, it's called c, which is large, so that there is a factorization of certain small operators, and then there is a gap in the spectrum. So this is what is somehow crucial for this semi-classical bulk gravity interpretation of a CFT. It looks like. But this statement does not in itself involve the notion of gauge invariance. I stated it in terms of this within code single trace operators, but it's not necessarily the case. It's not, at least it is, at least in my understanding, it is not necessarily the case that these operators, these single trace operators, have to be traces of some gauge group. It's not completely clear, I would say. Okay, so so that.
Because that this group will be SOD, right?
So no, SOD, 2 invariance is basically a global symmetry of the theory. So what, in a theory, global symmetry basically just organizes the states and the operators in some suitable way. They will arrange it in multiplets of that group. But if you have a gauge invariance, you only have singlets of that group in the theory, in the operator spectrum of the states. So that's the difference. So gauge invariance is essentially a redundancy in the description. It's not organizing your states and operators in any multiplets. It's just only the singlet will be present. So SUN is a gauge redundancy. The SOD, 2 and the global symmetries on both sides have to match. Okay, so there is no remnant of SUN invariance on the bulk side. There is no remnant of bulk diffeomorphism like invariance on the boundary side. Because they are the only singlets of both of these things need to be matched across the duality. Okay, but global symmetries are real genuine symmetries that organize this theory, organize the spectrum and operators of the theory, so they need to explicitly match between the two sides. Okay, so that's the structure. So anyway, yeah.
Global symmetry on the CFT side is global.
Yes. I mean, well, so global symmetries on the boundary side, so on the boundary CFT side, or on the CFT side, become gauge symmetries in the bulk, which asymptotically become global symmetries. Okay, so there exists global symmetries because the symmetries of the theory need to act only asymptotically in the gravity description. So there is no bulk. Bulk is some sort of a fictitious entity, right? So it's part of diffeomorphism invariance or some bigger symmetry of string theory. So, but there is that symmetry on the gravity side as well. That's the crucial point. So there may be a gauge field that you can associate to some global symmetry in the boundary, but it should have an action on the entire space-time, which corresponds to the global symmetry of the dual theory. So another way of saying the same thing is that gauge theories, even in general, at the boundaries of space-time, they become global symmetries, even in standard gauge invariance. Okay, so standard gauge theories, and that's, if you have looked at theta vacuum of QCD, for instance, that's associated to that. Okay, so yeah.
You're saying that the theory of the boundary need not be gauge invariance.
I'm saying that at least the way I presented it, it need not be. All known examples of the theories have gauge invariance, and it's a mystery. I would say it's a mystery why it is the case. And in string theory, for instance, the theories that we get, the n = 4 superangles has a gauge invariance. But it seems like somehow what seems to be, so the gauge invariance seems somehow to be going into the factorization structure as well as the gap in the spectrum. So that's somehow an indirect thing. But it looks like what is directly relevant for the semi-classical bulk-Einstein interpretation is the factorization of the low-lying states as well as the gap in the spectrum. Not the fact that the low-lying operators are somehow single trace constructed from gauge theory. Okay, so that it does, at least it may be, but I don't think we also understand the statements that I made last time with sufficient precision to make a statement. I don't think we understand it that well. You know what I'm saying? So we have this general structure seems to be true for all the Einstein gravity duals, but I don't think we understand them sufficiently well to make a very clear statement about the role of gauge invariance in it, the boundary gauge invariance in it.
My question was, if there were theories which didn't have any gauge symmetry,
Yeah.
would there be a dual string theory in the
It may, we don't know. It's all the examples seem to have some form of gauge invariance on the boundary. So, but we don't really know. So this is one reason I think it's a very interesting and important question. So the role of boundary gauge invariance, it seems to be somehow structurally present in all the string theory examples we know, but it seems like its role is not sufficiently clear. I think it's a very interesting question, but I don't think we have, people don't generally seem to care about boundary gauge invariance. I mean, it's not that they don't care about it, I don't think they have any ideas. You know what I'm saying? So it's like, yeah. So, but this, yeah, I mean, okay, there are many things one can say. Hi, welcome back. So I think, yeah, so I think that, any other questions? So, yes. So, okay, so I was going to ask you some, general personal questions, but I remember the camera is on, so let me not do that now. But anyway, so, okay, so I think so we kind of had like a review of ADS-CFT. And what we will do is, yeah, so we'll continue. So what we'll do is we'll basically use, Euclidean gravity calculations. So now we are going to kind of shift gear a little bit and make some statements about black holes in ADS. Okay, so this is what we want to do. And so black holes in ADS and how they connect with the gauge theory or the CFT description is what we want to kind of talk about. Okay, so let me start with something that I had kind of was hoping to avoid, but so we talked about Euclidean path integrals a lot, but my goal was mostly to use that as a tool for deriving Unruh effect and things like that, or Hawking, the Hartle-Hawking state and so on and so forth. That's how I used it. But so in that sense, you could think of that as a quantum field theory, either quantum field theory by itself or quantum field theory in a fixed background. So that's the context in which I was doing it. So I was trying to avoid talking about Euclidean path integral gravity and just somehow, but I think it is sufficiently useful, and it's in the last few years, its power has somehow enhanced in some ways. So I think I will actually discuss it. Okay, so what is a Euclidean path integral for gravity? So first of all, path integral for gravity is ill-defined for various reasons. Okay, so even more than, for instance, standard quantum field theory path integrals. Quantum field theory path integral, we don't seem to really know how to break down all the field configurations in a useful, mathematically precise sense, but conceptually at least it sort of makes sense. But in the case of path integral for gravity, the point is that if you have a metric g mu nu, you can always rescale it by some function of this kind. And if you're integrating over every field configuration involving the metric, you essentially are integrating over every possible e to the phi as well. Okay, so every possible, so this is called the conformal mode of the metric. So if you're integrating the path integral over all the metrics, conformal mode is also part of the integration. So, but if you make this change of variable into the action, Einstein action, what you will find is that this phi will pick up a kinetic term. So if you rewrite your Einstein action, R of G, root whatever this thing, root G R. So if you do this, it's a small exercise. It's done in, for instance, in the context of string theory in Polchinski, for instance, you can find calculations of this kind. It's fairly straightforward. And even in Birrell and Davis, you can look it up. So if you do this, you will find that the phi acquires a kinetic term, but it has a wrong sign. Okay? So the wrong sign means that it is unbounded from below. So it's in that sense, so this is sometimes called the path integral for this in some sense is just immediately not well defined. So we don't really fully understand how to make sense of Euclidean path integral in gravity directly. So I'm talking about a pragmatic problem. Of course, there is a bigger issue if you want to really think about it conceptually. It's not completely clear that, in some full theory of quantum gravity, it's not completely clear that the metric is the right degree of freedom to integrate over. Okay, because you have a string theory, or for instance in n equal 4 superangles theory versus ADS CFT, the path integral is the correct path integral for gravity is the CFT path integral, which is well defined, but it doesn't show anything about the bulk metric. You know what I'm saying? So, but if you would like to define a path integral in the gravitational variables, this is sort of a starting thing that one could try. But if you do that, what you find is this problem. This is called the conformal mode being, the Euclidean path integral for gravity is unbounded from below. Okay, so this is a problem. So there are issues of this kind. But what people typically do is that and I think that. What people typically do in these kinds of settings is that we oftentimes reduce the phase space over which we actually do the integral. Okay, so instead of trying to do the integral over the entire metric, space of metrics, you will try to choose some particular subspace of the space of metrics and hope that the integral is well defined. That's one strategy that people sometimes do. This is called the mini superspace approach to path integrals in quantum gravity. Okay, so this has some uses, and for instance, I think Gaurav, etc. work on this kind of thing. But there is another approach which is even more kind of draconian. You just don't try to do the path integral at all. And instead what you do is that you use this philosophy that if you are doing a path integral, generally speaking, the dominant contribution is going to come from classical solutions. Okay, so what you do is that you, instead of doing this integral, so if you really wanted to do this integral, becomes unbounded. So let me just write it here. From below. So for instance, the Hamiltonian is not well defined if you think of it that way. Okay, so it's a direct calculation. You can just check that the kinetic term will have the wrong sign. So yes. So let's define the Euclidean path integral. How one might, at least formally, this is the kind of object that you would write down. Okay, so this is some Euclidean action containing this phi stands for every possible other matter field, whatever else you want to include. So we just specialize, the metric has some special status, and SE, the metric part of it is, we'll write it like this. So this is some dot stuff with matter and so on, and we are right now working in flat space. Okay, so I'll start with flat space and do an old calculation of Gibbons and Hawking first, and then from there we'll go on to ADS where things are better defined, and there we will have something to say about So flat space basically means that what in the low energy theory does not have a lambda. So if you have when you say that the theory is flat space or ADS, what it means is the ground state is flat space or ADS. And the theory that is defining is either asymptotically flat or asymptotically ADS. Okay, so so that's what it means. So the metric is integrated over everything, but it has to be asymptotically flat. So whenever you say path integral of this kind, you need to specify boundary conditions. This is one of the main messages of holography and everything, So, and that's another important thing here, which is crucial for that, is the introduction of boundary terms. Okay, so these boundary terms will be important to make sense of these actions and so on. Okay, so since this object is not well defined, and this is kind of like, another spectacular, simplification that Hawking came up with, which is that he basically just assumed that, since we know that classical solutions are the dominant contribution to the path integral, let's just assume that this is essentially equal to this, plus corrections which are loop corrections, which you might choose to compute in some cases, but may not. Okay, so you just assume that there are some classical solutions which are the dominant contribution to the path integral. So, and then compute its classical action, exponentiate it, and that's basically your partition function. Okay, partition function or the Z. So right now, it will become a partition function when I demand that the asymptotically, the boundary direction has a periodicity in time. Okay, so this is basically what Hawking said, and if you have multiple classical solutions, you will have to pick the one with the least action, so that's the thing that dominates the ensemble or this partition function. Okay, so that's the idea. So and we will specialize. So at this level, so what we are going to do is we are going to say that tau is, so the boundary. So one thing that, so you know, in order to make such a statement, you need to have some notion of, let me erase this first. So you need to have some notion of boundary, and which we will take to be some kind of an R coordinate going to infinity. Okay, so some suitable notion of far away exists, and there is R is going to infinity, and so the idea is that at the, in all the other coordinates means like the, the t or the phi or the x or whatever other coordinates that you have in the geometry, they have this one particular time direction which basically has a periodicity of beta. So because that defines, so this is essentially the definition of canonical ensemble in gravity. Okay, so essentially what you're doing is you're saying that there is a partition function or a path integral which has asymptotically the periodicity of beta, which fixes the canonical ensemble with temperature 1 by beta. So this is your prescription. So this object, the way, with these understanding, this is a complete definition of canonical partition function, and the question is whether any of these objects, when you actually calculate them, do they make sense? Okay, so that's the starting point. Right. So the point is, yeah, so this G bar and phi bar has to be thought of as classical solutions. Okay, so this was integrated over everything. Here we are just looking at the saddle. Okay, so let's look at, so to warm up and do the old calculation, let's look at Euclidean Schwarzschild. Okay, which is nothing but, we have written this many times before, plus r square d omega 2 square, and the tau has a periodicity of what was it, 8 pi m? Did I write it somewhere? Yes, tau 8 pi m. Okay, so and this is the crucial point, is that this you obtain. So there is one more ingredient suddenly goes in, which is that you now are declaring that the geometry has to be regular in the interior. Okay, so you're only going to consider these classical solutions which are regular. Okay, there is no singularity that you're allowing. So, and that's what fixes this tau this way, and so once you have that, the point is that you can compute this action, and we will do that in a second, but at least in principle it should be clear that if you know the solution, this action should be well defined. There are problems coming from the fact that you're integrating over the entire space-time, and there are divergences coming from this R going to infinity limit, the boundary of space-time. So there you have to worry about boundary terms and some other subtleties. So boundary terms and counter terms. So I'll explain what they are in a second. So those things we have to worry about in order to kind of balance this divergence to make things finite. But given those things, it is reasonable that if you have a solution, you can compute its action, and then you can compute, once you know the partition function, you can, the standard canonical partition function, you can compute all of these things. These are standard formulas from, statistical mechanics. So you can compute your entropy and mass or energy like this. Yeah, so the word counter term is not, I don't know whether that's the word that Gibbons and Hawking used, but it's essentially like in light of ADS-CFT, when you go to ADS and ADS-CFT, you will see that these are genuinely counter terms, and in fact, the calculation is better defined in ADS. So, so the calculation that we are going to do now is a bit ad hoc, and I don't know of a completely watertight way of doing that calculation. The original calculation of, this is in the boundary. So this statement that I'm making here is basically defined in the R going to infinity limit. So this is the statement. So the point is that the asymptotic periodicity defines your ensemble, basically. So the canonical ensemble at temperature T equal to 1 by beta is fixed by the asymptotic periodicity of the spacetime. Not the periodicity in the bulk is sort of dynamically determined. We'll see. Okay, so depending on the solution, etc., and the smoothness in the etc., will fix it. So we will see. So when you say regular in this, so you mean just getting the conical sigma? Yeah, and I'm just going to, so we already did this sort of a calculation in Schwarzschild. When I get to ADS, I'll just leave it as an exercise, but it's the exact same thing. There's no difference. Okay? Yeah. Yeah. It would be like if you are in a microcanonical ensemble or something. So, so the question is, partition functions in general in Euclidean signature, I don't know how to make sense of them. So you want to ask a question. So yeah, so in a sense that question would require you to talk about microstates of gravitational systems. You know what I'm saying? And that is something that generally speaking we don't know how to access. See, another way of saying the same thing is this. So whenever you define a partition function z, you always, this is usually a functional of some object at infinity. Right? So some object at infinity, or in field theory it will be some functional of a source. So it's essentially that sort of a specification is what we are doing here. So the boundary values of the metric have a natural interpretation in terms of sources, especially in ADS-CFT kind of context. Okay? So you could think of this, so it is, so maybe you can ask this question after I discuss ADS-CFT. It's a bit better. So, but fundamentally, I don't think I will be able to answer it in a completely satisfactory way because these things are semi-classical things. So we do what we can at some level. You know what I'm saying? Of the full partition function, how to make sense of it with arbitrary boundary conditions at infinity, I don't think we know how to do it. You know what I'm saying? Because it may not be fully meaningful in gravity. Because meaningful in the sense in semi-classical gravity. You might need to specify all the values of fields in string theory at infinity or at the boundary of ADS to make that a completely well-defined question. So when we are talking about semi-classical gravity, so we are, doing certain, we are making some, we are considering classes of states in some sense, and that's why ensembles are sort of meaningful. Okay? Okay, so, okay, so that's our action. So that's our solution. So now what I'm going to do is I'm going to introduce a boundary term for our okay, so now we want to calculate this action, and I want to show that, okay, can I compute these things explicitly? Because we have, this E should basically, we know from, even though I have not shown you, this mass that shows up in the black hole metric is actually the physical mass of the space-time. So that's something that you can show in, canonical general relativity. So this calculation, if it is reasonable, should reproduce that. So if I compute this by computing this action in this particular way, I should basically end up finding the area by area law here, A by 4, and this should be M. So that's a check of various proposals, or that's kind of like a consistency or sanity check of my of this whole picture. So in order to do that, first thing we need to introduce what is called a Gibbons-Hawking-York boundary term to make the classical action for gravity well-defined in a variational sense. So let me write that down. I'll just write something down. I'm not going to be super well, I guess I will be more or less precise. So this is the boundary. So this is d3x and this is some k. Okay, so this quantity k. So right now I've not introduced the counter terms. So I'm just making boundary terms. I'm introducing boundary terms for gravity so that the classical variational principle is well defined. So if I want to, so I'll explain what that means in a second. So so let me just explain what this is first, and then I will tell you why it is interesting or useful to add it. Okay, this is the Gibbons-Hawking and York, and York is the first guy to do it, but I think Gibbons and Hawking kind of introduced it in the context of this path integral type calculation. That's when it became kind of took off in some sense. Okay, so the York had it, I think, a few, maybe almost a decade earlier, but this is so its power was fully used by Gibbons and Hawking. Okay, so what do I mean by, you know, a boundary term for gravity? So what I really mean is that, let's say that you are introducing some cutoff, okay, at some large r. This capital R is supposed to be some fixed value but large, okay. So, and if that is the case, I can define an induced metric on, you know, or maybe better still, h mu nu is the metric at this cutoff. Okay, so note that this is in principle, we don't have to, you know, this construction that I'm going to write down for this k is actually much more general than this particular cutoff. We are interested in putting a cutoff in large R in the Schwarzschild black hole, so we are going to specialize that a little bit. But in general, I could define any surface in space-time and then talk about variational principles of this kind. Okay, so and there this will not necessarily be the embedding equation for the surface. Okay, so what you would really oftentimes do is you will write some equation which is phi of x mu is equal to 0. So if you have one equation connecting 4 variables, then you have a codimension 1 surface. Okay, so or you can, another very useful way to do this is to say that x mu, you define your coordinates in terms of some ya, where mu are the 4 bulk coordinates and a is going from 1, 2, 3, so that basically you have an embedding of the 4 space-time coordinates. So yeah, basically this surface ya is being embedded into the 4x mu coordinates. So this is another way to think about it. Okay, so if you have all 4, so this is sometimes called the parametric way of writing the thing, and this is basically the equation for the surface. So this is a parameterization of this surface. It's the same surface. Okay, so because the surface is 3-dimensional, there has to be 3 parameters, and those 3 parameters are what we call the coordinates of the surface. Fine, so these are sort of equivalent way of writing it, but I am specializing to the case where this equation is basically r minus capital R is equal to 0. And there is no conditions on t or phi, or t or theta or phi. Okay, so this is purely a function of the small r. There is no dependence on any coordinate other than small r here. All right. So anyway, so the induced metric on this surface is basically g mu nu at phi equal to 0. That's what is called the induced metric. Essentially, you plug in these conditions into the metric and then write out the explicit form. So you will get a 3-dimensional effective metric. So if I plug in x mu of ya into this here, the number of independent coordinates here will decrease by 1, right? And you will get a 3-dimensional metric. So that metric is what I'm calling the induced metric h mu nu. And in the case of r equals to capital R, it's trivial. It's completely simple because the r component just drops off, and you basically get 1 minus. So in this particular case, your gij is ds square induced, if you like, is 1 minus 2m by capital R d tau square plus capital R square d omega 2 square. Fine? So now what we want to do is, so I'll just make the general definition of this k, but we can compute it in fairly simple ways for our case. So the general idea is that you introduce a normal vector n mu. Okay, the n mu is defined basically as d phi by dx mu. Note that the index here is downstairs. That's very important. Otherwise you'll make mistakes. Okay, because it's defined as a gradient of the function that was used to define the surface, and the gradient comes with x mu in the upstairs in the numerator. So this n mu is with in downstairs. So and in this particular case that we have here, it basically takes the form 0, 1, 0, 0. Right? Because its phi is just r minus capital R, small r minus capital R. So if you d phi by dt is 0, d phi by dr is the only non-trivial guy, all the others are 0. Okay? So, right. So the point is, so now what there is an object, it's called the extrinsic curvature that I define so let me also define a new useful quantity, which is a projector. Okay, so we just defined like this. What it really does is that if I have a quantity which is well defined in the mu nu coordinates or in the full space time, I can project it onto the surface by taking this, let's say the g mu nu there, and project it onto by doing this, and I'll basically get the induced metric, for example. Okay, so this is essentially what we are doing when we are plugging it in here. Okay, so this essentially what you're doing is multiplying by these factors onto this. Okay, that's essentially what you're doing. So you will get this HAB or HAB to be, your HAB is going to be GAB times, G mu nu, so let me call it I. G mu nu, E mu I, E nu J. Okay, so this is the induced metric. In practice, that's what happens. So, and now I have all the tools to define what I call the extrinsic curvature, which is okay, so this is the definition of what is called the extrinsic curvature K. And so I'm not going to tell you why this is called the extrinsic curvature and so on. You can just view it as a definition, and for my purposes it's not even important that it is an extrinsic curvature. Some quantity, and I'll tell you why it is useful for us in a second. So this is some definition, and the point is that this is now completely calculable. I want to really emphasize that. It's just, you can plug it in and check. And in fact, all this full generality is not really necessary for us, but it is somehow more cleaner if you define it that way. That's why I did it. But once you have that, it's just a straightforward calculation. You can compute it, and you have the inverse of this induced metric times Kij is what is called K, and that's what is going in here. Okay, so now at that stage, I have completely defined this action. Any questions?
So this extrinsic curvature is not the same as Riemann curvature?
No. So the Riemann curvature doesn't care about how the surface is embedded in the ambient spacetime. Here it does because of these E mu's. So this basically is roughly telling you how the curve surface is turning around in the embedding thing. So you can have extrinsic curvature while the Riemann tensor is 0. So for instance, if you compute a cylinder, embedded in Minkowski's or Euclidean space, it has 0 Riemann tensor curvature, right? Because it's just a flat thing, you have just rolled it. So this is flat, and you roll it, you'll get this, but its extrinsic curvature is non-zero. So, and that's what this is. Okay, so yeah, but it doesn't really matter. For our purposes, I just want to make the definition sort of complete, so that in case you want to actually calculate something, this is enough. This is a complete definition of K. Okay, so the reason why we care about it is not so much because it is extrinsic curvature or whatever, but the point is we want to have a well-defined variational principle. So a well-defined variational principle means that when you vary your action, which is root g r, let's say, typically in Einstein graph, not typically, if you just do this computation directly, you will find that this is in the bulk manifold M. You will find this is essentially g mu nu. Maybe there is an overall factor, which may be a half or something, and then you have root g times delta g mu nu. Okay, so this is the place usually where we stop, because what we typically do is that we assume that you have to do some integration by parts in order to get to this, and you will assume that the boundary terms coming from it are always dying down. Okay, but that need not be the case if your boundary is at finite radius. If you are sending all the fields are dying down at infinity, then it's a reasonable assumption. But if you want to make a completely well-defined classical physics problem, then you also have to worry about how, you really have to make it sort of more precise. And in particular, by doing it, you can define this at some finite radius. Okay, so this is the rough idea. So if you keep track of those explicit terms, and this is a slightly lengthy calculation, but I'm sure that you have seen similar things in GR course, stuff times delta g. When I say delta g, I mean delta g mu nu. Okay, it's not plus some other dm. Well, I mean, yeah, that's fine. Stuff prime delta d of delta g. Okay, this is the structure that it will have. So essentially, because it's a second order differential operator that is sitting inside Einstein's action, so when you do this variational calculation, you will find that there is one term like this and one term like this. Okay, and this is not considered to be a good setup for variational principles. And the reason is, when we say variational principle, what we typically want is that we hold, so a second order differential equation has two pieces of data, right? So it has two pieces of data. So if you kill off both, you don't, if you're okay with specifying, let's say, the boundary value of G. But if you also specify the derivatives of G at infinity, then there is only one solution, because it's a second order differential equation. You know what I'm saying? So then there is no trivial, the dynamics is trivial. So you don't want to have to specify this and this in order to extract an equation of motion by a variational principle. So what you would like is, you would like to kind of have, so in standard scalar field theory, second order scalar field theory, you will find that there is only this term that comes up when you do the variational principle. Einstein's action is a little bit weird or strange, or has some unique properties of this kind. I mean, we can talk about why, but the point is that at the end of the day you get both of them. So if you demand both of them to be fixed at the infinity or boundary, then you have no dynamics, so we don't want that. So we need to add a boundary term explicitly to the action, so that that guy will kill off the second term. That's what this guy is doing. So you can do the variational principle for the Gibbons-Hawking term, and you will see that this guy dies off. Okay, so if you add, so delta of root GR, I'm being very schematic, plus K, I'm not, this is M and this is dm, then you basically get the bulk EOM, which is Einstein. Okay, let me just write it as G mu nu term, plus this is in the bulk, and then there is on the boundary, you will have something times delta G. So this is the structure that you will have. So now you have a well-defined what is called a Dirichlet problem. Okay, so you can hold the value of the metric at some cutoff or boundary fixed, and then you have a well-defined variational principle. You can get your equations of motion, and so then you're happy. Okay, so this is the setup. So that's the reason why we add Gibbons-Hawking term. Okay, so now with this Gibbons-Hawking term, you can, Gibbons-Hawking term also put into the metric. So I wrote down the metric for the Euclidean Schwarzschild, right? So you can compute the action. Now you can compute it with some r equals to capital R cutoff. Okay, because we have put a cutoff, you will get a finite answer guaranteed, and because of the boundary term, it will get some extra contribution. Okay, note also that because Schwarzschild is a solution of Rij equal to 0, it's a vacuum solution, right? Which means that this R is 0. So without this boundary term, you will get 0 as the answer. Okay, in flat space. So you need both of those things to get, so the boundary term is crucial. Okay, so yeah. So now let's write down. So I'm just going to, now that all the ingredients are there, this is just a straightforward calculation, and the result of the action for, if you compute the Einstein action plus the Gibbons-Hawking term, you will find that your total action, so S Einstein plus S Gibbons-Hawking York, is going to be okay, so this R is the cutoff, not the Ricci scalar or anything. Okay, the Ricci scalar is 0. I mean, I probably should have used another letter. So, and note that the beta is happening because there is a periodic integral. Okay, so note that the nature of the integral is basically that you have a d4x root g times r, roughly speaking, right? So at some particular r equal to capital R, you basically only have an integration on the other guys. So the d3x. So there is a tau integral which gives you a beta, and the rest of the stuff, there is some r dependence in it. That's capital R dependence, and that's how you get this explicit expression. Okay. So the problem with this expression, of course, is that it has a cutoff dependence capital R, and we don't know how to completely systematically take care of it. And I don't think actually the complete answer for flat space is actually, I'll give you a sort of a hand waving answer that Hawking used, which gives us a right answer, but I don't think there is a completely satisfactory answer for how to do this subtraction in flat space. Okay, and there are deep reasons why I think that it is actually, it's probably not the correct thing to do at some level. But this is something that works, and in ADS we will make it more precise. In ADS it is legitimate, it's truly legitimate to do the subtraction in a certain way that I'm talking about. Okay, so now what we are going to do is we are going to do a counter term. Okay, so this counter term is very naturally well defined in ADS. Okay, so but what I'm going to do here is more like a background subtraction. So there is no, so this is what Gibbons and Hawking did. So this is my root h times k plus so what we'll do is we'll subtract a specific k, okay, or you can actually make it a little bit simpler and collect it into one piece, and this is k minus k naught, okay, and the k naught, so this is defined as the extrinsic curvature, the k curvature of the same Hij, but now embedded not in Schwarzschild but in empty Minkowski space or Euclidean space. Okay, so this is what k naught means. So let me say what that actually means. So ds square on the r equal to capital R surface that we had was 1 minus 2m by r d tau square plus r square d omega 2 square, right? This is what we got from demanding small r equal to capital R on some particular slice of Schwarzschild. So now what we want to do is we want to think of this as being embedded in Euclidean space, the Euclidean flat space. So, and what does that mean? That basically just means that we are going to think of our G mu nu as not as Schwarzschild but as some ds square, let me call it datum, because we are going to subtract using that, is just 1 minus 2m by r d tau square plus dr square plus r square d omega 2 square. Fine? Is that clear what is happening there? So I'm taking the exact same thing, but it's the exact same thing, but I'm embedding it in Euclidean space. Okay, so this is the metric on the, if you started with my Schwarzschild and set small r equal to capital R, this is what I will get. But now I'm taking that and I'm embedding that into flat space. Note that this 1 minus 2m by r being a constant, it doesn't affect the curvature of the space-time. So that's why this thing is just, this is just a rescaling of tau effectively. So, but this part is what matters. Okay, so here now it is r and this thing. I'm embedding it into Euclidean space, Euclidean polar coordinates essentially. Okay, so now I can do the exact same calculation of the extrinsic curvature and the Gibbons-Hawking term, etc., and I can do the same sort of calculation, and I can get this k naught. Okay, and the result is what you find for so see, the Einstein piece was 0 because r is 0, and this is what contributed to this.
K0 is a 4-dimensional curvature.
No. K0 is 3-dimensional, right? Because this integration is on dm.
But we have 4 different coordinates in the.
So this is the embedding. So this guy is the Hij, right? And this Hij came from Gij, which was Schwarzschild. Fine. And then what I'm saying is that I want to embed the same surface, but now in empty space, and that's what this is. This 1 minus 2m by r by times d tau square is a piece of Hij. It should not be thought of as part of that's just a constant d tau square like term. This is capital R, right? So this is the place where this is a 4-dimensional embedding Euclidean Minkowski space. Fine.
We are taking the.
So let me explain it this way. Maybe if you set r equal to capital R here and here, you'll get that Hij, right? So this is Minkowski space, Euclidean Minkowski space. So that means that I have embedded this surface into that in some way. Okay? I mean, you could ask questions about whether it is a unique embedding, etc., but I don't think there is much of choice there. So I mean in ADS it will become better anyway. So here, yeah, so I mean you could ask whether there is a unique embedding, so I haven't really thought about it, but I suspect I will leave it as an exercise. You know what I'm saying? So I think, but but there is one canonical and simple embedding sitting there, which is R equal to capital R, right? So and that's what we are doing. I don't think, yeah, I don't know. I mean, yeah, there could be a question about uniqueness there, but I feel like it may not be. There may be a way to argue around it. But yeah, so let me not try to, you know, defend it too much, because anyway, I don't think it is very defensible. You know, some of these things that we're doing right now. Okay, so yeah, so anyway, so this was for the Gibbons-Hawking York term. Now we can do the exact same thing for this counter term. So essentially, there will be a, so now we want to compute SE plus SGHY plus S counter term. Okay, and this counter term is nothing but 1 by 8 pi G times root H K naught. And this you can again calculate the same exact way, and you will find that it is 8 pi capital R minus 8 pi M. Okay? So you can clearly see that when you put these two things together, this the divergent thing vanishes. Okay? So yeah. So the counter term is plus, and this is this. I think there's a minus sign here. And okay, also I forgot to mention, there are some terms which die down as R goes to infinity, also here. Okay, but they don't matter, because anyway in the, so what we are going to do is we are going to do all this, and then we are going to take capital R going to infinity. And because we have a finite answer, we will still be left with it, because all the other terms are somehow subleading. Okay? So now we have, so now you just add all these things together, and you will find the total action, or the total partition function. So the canonical partition function of gravity, which is, if you do this, you find this is beta m by 2. Okay, which is the same thing as 4 pi m squared. Fine? So, and this means z of beta, which is e to the minus se, evaluated on this classical action, is e to the minus beta square by 16 pi g. Okay? I think I have set G Newton equal to 1 here. So let me just set G Newton equal to 1. Sorry, what are you saying? SE is the sum of all three terms, yes. It's not correct?
So would that be the minus n? Because there is a minus 12 beta, because
no, minus 12 beta, yeah, so maybe I'm missing some sign here.
Because 8 pi r will be cancelling from both the sides.
Mm-hmm.
This will be coming with a plus sign, and that will be a minus.
Maybe this is plus here. Yeah, so no, so there is, this has a 1 by 16 pi g sitting up front, or 1 by 16 pi g here. Okay, and so this 1 by 16 pi g I forgot. So, and maybe the minus sign is here and the plus sign is there. Is that possible? So minus, no, there is a minus sign here. So I think we are fine. So this is minus 1 by 16 pi g sitting there. And so you will also have, you know, so this basically means that this will flip the sign. So this will be 16 pi g, and there will be a plus here. Okay, so basically I forgot a factor of minus 1 by 16 pi g everywhere. So, and if you add all of them, and then I'm setting g equal to 1, hopefully you should get this. Okay, and so this is my final answer. And the usefulness of this is that now I can use my canonical ensemble results to get, this will be 4 pi m square. What, sorry?
This is total distance. It's not distance, it's total distance.
Yeah, so I think this, let me just call it Einstein-Hilbert here. So this whole thing is, SE is the thing that I originally wrote, which is the total whatever action that goes into the path integral, okay? So that EH stands for Einstein-Hilbert. This SE stands for S Euclidean. Okay, so the Euclidean gravity action, whatever it might be, which contains the boundary terms as well as the counter terms. And then I have this expression, which gives me 4 pi m square, which is a by 4. And E, you can check, is again m. So we have, so this is a famous calculation of Gibbons and Hawking. Okay, it's a very famous calculation. It's especially at the time when they did it, like all of these things are kind of shady things, you know. And it takes some sort of courage to do these things. But somehow you got the right answer. So Hawking was somehow on the right track. So, and we'll see that this gets better in ADS. So, right. Okay, any questions? So we are going to switch gears and now go to ADS.
There's no reasoning for the counter.
It is sort of a reasoning, right? I mean, it's a background subtraction. You know, so you're subtracting what this, so somehow you're treating the screen as more fundamental in some way, and the embedding in you know, whether it was initially in Schwarzschild to be sort of incidental, and then you are subtracting with respect to what can be called the vacuum state, which is flat space. So, but the one reason why I don't like it is because in flat space, there are very good reasons, for me at least, to think that these should really be viewed as infrared divergences. In ADS, the dual theory is naturally interpreted as an ultraviolet divergence. So in infrared divergence, it's not so meaningful to regulate in the same way that we do in quantum field theory. So the reason why the ADS calculation, this counter term is a natural thing, because the ADS divergences have a very natural interpretation as UV divergence in the CFT, and so it makes sense to regulate it by using a regulator. So if the CFT is well defined in the infrared, the ultraviolet regulator should not matter. But that's not the case here. Here it is more natural. So when you have infrared divergences, you know, it's more natural to define quantities which are better, called inclusive quantities. For instance, scattering amplitudes, you define these, instead of looking at the bare scattering amplitude, you'll define an inclusive scattering amplitude. So that's actually a better thing to define. So this is somehow telling us that this is not quite the right quantity to compute, in my view. You know what I'm saying? So, but yeah, so these are, in flat space, these are better thought of as infrared divergence. That I'm very confident about. It's not a widely known fact in my opinion, or widely appreciated fact, but that I'm very confident about. So, so in that sense, that it's also a fact that there is, I don't think anybody has come up with a completely satisfactory way of doing the subtraction. You know what I'm saying? So both these facts taken together, in my mind, is a suggestion that there is a better way to do this. So, okay, so, but now let's go to ADS CFT, and so so what I talked about last time, most of my discussion, and in fact most of our focus in many purposes would be in Lorentzian ADS CFT. Because Lorentzian ADS CFT is interesting because that's where information paradox and various other real-time things will show up. So that's, I've mentioned that before. But ADS CFT in some sense is easiest to formulate in Euclidean space, Euclidean signature. And in fact, that's where the original, right after Maltasena's derivation was more in the context of, black brains, and they had a Lorentzian time. But one of the main things that Witten did was to recognize that if you go to Euclidean signature, this holographic interpretation becomes very transparent and simple. So what I'm going to write down now is sometimes called the GKPW dictionary of ADS CFT. Okay, so what I wrote down in the last lecture was actually something that was written down later in Lorentzian signature by Banks, Douglas, Horowitz, and Martinich. Okay, so that is basically the statement that if you are looking at Lorentzian signature, the only meaningful mode that you can define is a normalizable mode, and the boundary values of the normalizable modes are basically giving you operators directly in the CFT. Okay, so that's the statement. I want you to kind of keep that in mind because I'm going to do a different prescription here. Okay, so if this is in Lorentzian signature, Lorentzian ADS CFT if you like, and the prescription is that in Lorentzian ADS CFT, there are two modes. Like in any second order differential equation, there are two modes. One of them is the normalizable mode called the normalizable mode, which I said which has finite energy, and then there is another which has divergent energy, which is called the non-normalizable mode. Okay, there are two of them. So what we do in Lorentzian ADS-CFT is we set the non-normalizable mode to 0. So then the only solution, the only freedom that you have in ADS-CFT in Lorentzian signature is the freedom to choose the normalizable mode. And what you do is we take the Lorentzian signature and we go to the boundary. So the claim is that this basically gives you a boundary operator. Okay, and this delta is basically, this is the map between the mass of the scalar field. I'm specializing the scalar fields, but the general statement exists for other fields as well. Okay, so this is the connection relating these two things. So if your mass of the scalar field is phi, this guy is, when you take it to the boundary with this particular scaling, because fields are dying down at infinity, so you have to compensate for that so that you get a finite value. So when you do that, you basically get an operator. This has the interpretation as a CFT operator. So this is a CFT guy, and because it has only x dependence, it makes sense, CFT operator. And this phi is in some sense the bulk field. Okay, so and this is what is called the extrapolate dictionary. So the extrapolate dictionary is what was written by BDHM. And this came actually after the Euclidean ADS-CFT correspondence, which is what I'm going to talk about now. Okay, so in some sense, this BDHM is sort of one of the legendary papers in ADS-CFT. I mean, the two papers. So this is Giddings, Kachru, and sorry, not Giddings. What is it? So Gubser, Klobanov, Polyakov. So there's too much time in desert space. So and this is Witten. Okay, so this is a standard prescription. So you can go look at these papers. I would say that Witten's paper especially is quite easy to read. Okay, especially in hindsight. It's in many ways, that paper is kind of like, what people have been doing for about 10 or 15 years after that is, I would still say, it was kind of footnotes to that paper. It's truly a remarkable paper. So, and it's very clean in some sense, So this is our extrapolate dictionary. So now in this dictionary, it's in Euclidean signature, and the Euclidean signature, the key point is that there is only if you demand regularity of the field in the bulk of ADS, then there is only one field, which is the non-normalizable mode. Okay, so what you say, so let me write down the correspondence. So now in Euclidean ADS, there is only the non-normalizable mode. Only non-normalizable mode. And the reason, see here also it is true that there are two separate degrees of freedom. But one of those if you interpret that as 1 degree of freedom, it will have a blow up inside the center, at the center of ADS. So if you want only regular field configurations, you only allow these non-normalizable modes. The normalizable, what used to be the normalizable mode in Lorentzian signature will basically blow up in the interior. Okay, so here on the other hand, both of them are well defined in the interior. So there's a property of wave equations in Lorentzian and Euclidean signatures. So this is something that happens. Similar things exist in flat space as well. Okay, so only the non-normalizable mode exists. So and Witten's prescription was that so Witten's prescription was that this non-normalizable mode, so let's write down the bulk field, which has the okay, so this is what the GKP dictionary says. So let me explain what that means. What it is really saying is that the non-normalizable mode has a different fall off, which is different from this r to the delta fall off of this normalizable mode. So you compensate for that by using this. Then you have a well-defined boundary limit, and the interpretation of the mode changes. So here the interpretation was that the bulk field, the boundary value, is the operator itself. Okay, but in the Euclidean ADS-CFT, the interpretation of this J is that this is the J that couples in the field theory as a source to this operator. Okay, so the boundary value of a bulk field in Euclidean ADS-CFT is basically a source for the dual operator. Okay, so this becomes a little bit more transparent if I write it in terms of a path integral language. So and let me just say that, yeah, okay. So this statement is slightly magical at the moment, but we'll, so I'll write down some expression which will make a little bit more sense. So let me make the statement whatever it is. The statement is that if you only turn on the non-normalizable mode, the asymptotic fall off of this field is different from this guy. So essentially the fall off is what defines the mode. Okay, so the asymptotic fall off of the solution of the wave equation in ADS has two particular kinds of fall offs. So the one of them is normalizable, one of them is non-normalizable, and if you have the non-normalizable, you have to scale it like this so that you have a well-defined boundary limit, and that limit is to be interpreted not as the value of the field itself or the operator corresponding to the field itself, but as a source to that field. Okay, so this is the prescription. So let me make it a little bit more plausible. So first what I'll do is, yeah, so let me write it like this. So the general idea is like this. So okay, let me actually write down a partition function in a general field theory. Okay, so a partition function in a general field theory with some source. So how do you define it? You define it, generally speaking, like this. This is in Euclidean, this thing. So let's say we are working with some scalar field phi. Okay, so I'm going to call the scalar field phi tilde to emphasize that now I'm talking about some digression in standard quantum field theory. Okay, so e to the minus, there will be some action for the scalar, which is as phi tilde, and then what you do when you want to couple it to a source is that, let's work in 4 dimensions and you'll have an action like this. Okay, so this is the definition of the partition function with source in any quantum field theory. Right? So this sometimes you will write in this way. In the theory, whatever the theory might be. So this is basically the expectation value of this particular operator evaluated in the field theory. Right? This expectation value just means you integrate with the insertion of this operator into the path integral. That's what expectation values mean. Fine? So this is two ways of writing the same exact thing. But this is what one calls a partition function in a quantum field theory. So let's specialize this to the case of a CFT. We don't have to do anything except we change the subscript like this. Okay? So note that this expression, what you're doing is you're basically computing the expectation value of the source term, this e to the minus j phi term, in the conformal field theory. And phi tilde is basically some field or operator in the conformal field theory. So this is a completely well-defined operation that one could do. Okay? So now this is for conformal field theory. So Witten's claim is basically that this object is should be viewed as the same object as J naught x on the boundary of the bulk M. So this whole theory is living in, let's say this is my M and this boundary is D of M, and my CFT is living in the boundary D of M. So I'm defining this said CFT, which is now to be thought of as living on DM. Okay? And the claim is that the gravity path integral, which we don't know what it is, right? Because we don't know, we need to know for the full string theory if you want to really truly define it. But this should be thought of as the same thing as the gravity path integral with fixed boundary values for fields at the boundary. Is that statement clear? So if the Euclidean gravity path integral is to be viewed as whatever are the fields in the CFT, but those, the sources for those fields are fixed. at the boundary, and then you treat those as the boundary values of your bulk fields and do the, whatever be the path integral for the gravity in the bulk. If it is semi-classical gravity, you do that path integral to the ability that you can. Or if it is some string theory thing, and if you know how to do all the things, then you do that. Okay, so this is a less well-defined object than this object, because bulk definition of quantum gravity in ADS is less well-defined. But is that picture clear? This is a very important, this is, in some sense, this is the ADS safety correspondence. The most cleanest version of the, or the original version of the ADS safety correspondence, which was in the context of Euclidean ADS safety. And we are going to use that in the context of black holes next. Any question? So this is what motivates the fact that, so here the key point is that on the boundary, this J was a source for the field. Okay? So that's the reason why it's natural to think of the boundary values of certain classes of fields, which are basically sourced by these non-normalizable modes, or which source these non-normalizable modes, as having boundary values which are non-normalizable, or which are sources. Okay, so this is the key. So this is sometimes called, this is sometimes called the differential dictionary, because if you know the CFT partition function as a functional of J, you can just keep taking, and you will get correlation functions. If you set this to J equal to 0. This is the standard formula for correlation functions in quantum field theory, right? So that might be a 1 by I to the n or something here, but this is in Euclidean CFT. So Euclidean field theory. So this is a completely well-defined thing. So and this is, so because of this fact that partition functions and correlation functions are connected via this differential equation, differential formula, this is sometimes called the differential dictionary. Okay? So note that this is, so here I started with the source for the boundary value of the field, but I'm getting correlation functions for operators which couple to that source in the field theory. Okay, it's not a, it's not a J thing, because J is not something that is really like, you can think of it as a probe on the CFT. You are kind of coupling the operator of the CFT to some J, and then J you have some freedom. You can, it's a functional of J. So for arbitrary choices of J of X, this object is well defined. So J is something that you have the freedom to move around. Okay, and the point is, if you know that, that means that this object is an extremely powerful object, and if you're actually able to compute it, you have solved the quantum field theory. Okay, in general, of course, you're not going to be able to do it. So which means that you can take these functional derivatives and you get these correlation functions. So the information about all the correlators of all the fields in the CFT are there in this object, if you know how each of those operators couple to their respective sources. Is that fine? So that's the reason why this is called the differential dictionary. And what you're doing is you take non-normalizable mode, boundary value gives you a J, a source, and because the partition function of the CFT and the gravity are connected in this way, you can compute this object. Note that this object is well defined but harder to calculate because it's in quantum field theory. You have to do, you have to do this partition function calculation for n equal for super Yang-Mills. Yeah, at least if you had an infinite supercomputer, or not supercomputer, quantum computer or something like that, you may be able to do it. But in practice, but on the other hand, this is a conceptually completely, we feel that we understand it. But this guy on the other hand, we don't know what it really means. It's basically a gravity object. All we know is basically the holography inspired idea that boundary values of bulk stuff is what is sufficient to define it completely. That's the only thing we really know about it. So this object then is equal to this is the claim of ADS-CFT. Okay? So yeah. Oh, I meant J only. So yeah, it's J. So it's just basically the boundary value of the non-normalizable mode. Any other question?
So what is the Z? Z for my studies?
Z, that I should have written R there. So, R and Z are two natural coordinates for, so let me, actually that's a good point for me to write. Sometimes this is what is called, so this is RD, and this whole thing is ADS-D plus 1 in Poincare coordinates. I wrote Poincare coordinates in as r coordinate, but if you just define, z is equal to 1 by r or L square by r, depending on whether there is a capital L sitting there, then you will basically get this. So it's just r going to infinity is z going to 0. So this is so r going to infinity or z going to 0. Both are the same. Z going to 0 is also the boundary of ADS. So in these coordinates, that's what the boundary is. So, and note that this is Euclidean RD. That's what makes us Euclidean ADS-CFT. Okay, and this Z is just a radial coordinate. Any questions? Any questions? So
taking this limit, we are ensuring that the fall off of the r to the power d minus delta is much stronger than how the phi grows up at the infinity.
Right. So the point is, when you say it is a mode, what it means is that you are solving the wave equation in ADS. So I wrote down the wave equation in ADS, like in last lecture or something, and with that choice, with that ADS wave equation, maybe in Lorentzian, maybe in Euclidean. So what you solve it, and then you will find two independent degrees of freedom, because the second order differential equation. And that independent degree of freedom is what is being captured by normalizable mode and non-normalizable mode. And the claim is that if you demand regularity in the bulk, the normalizable mode will get killed in Euclidean ADS. So if you only consider regular configurations in the bulk, only this will be left. And so that's, in some sense, makes the discussion a little bit easier. And that's why Euclidean ADS-CFT was first discussed, and this thing was discussed later. Okay, so and if you do this, so the point is that it's a property of the wave equations in ADS that the fall off of the two modes go like this. So at large R, the behavior of the field has to be either this or that, or some linear combination. That's the only possibility. So that's what we mean by the two separate modes. So note that it is different. So this is also one reason why, in some sense, holography in flat space is harder, because holography in flat space, it depends. So here you could take an overall r to the delta or r to the d minus delta and define a boundary value. In flat space, if you do this, you will see that the wave equations have dependence on the angular quantum number j. So you will have to do that more carefully, or at least, so it won't work that easily here. The radial coordinate is somehow universal here. It's already suggesting about some screen in some way. But that's not quite the case in flat space. Flat space, there is, you have to do a bit more work, but I think fundamentally it is sort of similar in some ways. But at least at a technical level, there is a difference, which is that if you solve the wave equation, and that's why you have 1 by r to the L plus 1 or whatever in your Maxwell's in electromagnetism, right? So 1 by r to the L and 1 by r to the L plus 1 are two different fall-offs, but that depends on the angular quantum number. So here it doesn't depend on the angular quantum number at all. I didn't even talk about separating variables. I mean, I can, and in fact, in order to do actual calculations, we have to. But here I didn't say anything about separating variables. I just said that the modes, there are only two modes, and those two modes nicely combine into just a function of phi of r comma x, which is a little bit of a surprising fact if you're used to flat space. Okay, there is no j dependence, there is no nothing. All of them basically just work very nicely. Okay, so and that's why you can separate it out in terms of the field itself and not its Fourier decompositions necessarily. The field itself you can work. Okay, that's another indication of holography. So that's another, all of the things that I'm saying here are in some sense, effectively evidence for holography, because there are many places where things would not have worked. So that's why ADS-CFT is in some sense such a robust structure. I think it is very difficult to argue against ADS-CFT. I mean, you could argue maybe the interior of the black hole is inside ADS-CFT or not. I mean, I think it is, but at least at the most basic level, the extent to which it is so solid is undeniable. So quantum gravity in ADS, I think you can call it a conjecture, but I really think it is n equal for superioris theory. So anyway, we'll talk about, so I think this is a good place to stop, because I don't think I have enough time. Despite my increased speed of speaking throughout the entire lecture, I don't think we have got to the end. So we'll talk about it tomorrow. At 10:30 we'll meet.